Good morning again, students. We are in module 2, and we under module 2 we have started discussion on elastic and plastic deformation in metal forming processes, and this we have discussed. Under this we have discussed engineering strain, then true strain, then what is the total strain. It is total your engineering strain is a summation of your elastic strain as well as your plastic strain. And in the metal forming processes, we have come to a conclusion, or come to the discussion that your plastic strain is nearly equal to your total strain. This is why, because your elastic strain is very small, much smaller as compared to your plastic strain, especially talking in the case of your metal forming processes. Okay, so this we have discussed. Then we took example of one case, that was tension and compression. I have corrected this PPT. Earlier it was -5, so the correct value is -0.5. Then we moved to true strain and then true stress strain curve. This we have discussed in module 1 itself. Okay. Then we tried to see the volume constancy during plastic deformation, and under this there was some typo error in the numerator part. The numerator and denominator got exchanged. Okay, so I told during the lecture that I will be correcting this, and this is the correct formulas. So here we can see your when we are considering your volume consistency or constancy, your stresses, suppose it is A, B, C. You can say length, width, and height. Okay, or X, Y, Z. Okay, so you can this may be XY plane, then Z is your height. Okay, C0 is your height. So here what we could see that by considering the volume constancy, because it is obvious that volume would remain the constant. So what was the conclusion? That the summation of all the three strains, that is along x-axis, y-axis, and z-axis is equal to 0. This we have concluded in the previous lecture. Okay, so I hope up to this there is no confusion, there is no doubt, and I have tried to make the PPTs in a self-explanatory mode, so that you need not to bother about books or any other notes after reading these PPTs. Okay, so from volume constancy, we could conclude your sum of your all strains along the principal axis, that is x, y, and z. It is equal to 0. Okay, so suppose in the case of along the x and y axis, if the elastic, if your total strain is positive, then obviously the strain along the z axis would be and we would have negative value, and vice versa. For today, this was basic introduction about elastic and plastic deformation. And today, in particular, when we talk about metal forming processes, we are basically interested in the plastic deformation part. Okay. So in today's session, we will try to cover in very short the mechanism of plastic deformation. Okay, how what happens in your materials, which is responsible for the plastic deformation of your metal material. Okay. So in today's discussion, we will try to understand what are the phenomena due to which your plastic deformation occurs. Okay. So going in depth, using your Hooke's law and other available literature, researchers have tried to compute your theoretical strength of your perfect crystals. Okay, so this work has been done from the long time, maybe 200, 3 years back. We are able to calculate the various strengths like tensile, under tensile, elastic proportionality limit, then elastic limit, and ultimate tensile strength. Okay, so we are able to calculate, we are able to find out these values in your earlier material studies. Okay, maybe 200 or 300 or maybe more than that, we are able to compute these values. Okay, but when we are comparing this theoretical value, this theoretical strength of your materials with the actual observed value of your material. So what is happening? The theoretical strength of your perfect crystal is many times as compared to your actual measured value. Okay, so since something we are calculating theoretically, because when we are calculating something theoretically, then we are taking ideal conditions, and we are thinking that your material structure, that is a crystal structure, is perfect. Okay, but we know, I think we have already gone through the material science course, that the material crystals that we expect for explanation, for understanding the metals that we take, that these are the perfect crystals, but in actual or in practical, these crystals are not perfect. They have impurities. It means they are imperfect crystals. Okay, so the theoretical strength of perfect crystal is obviously should be high as compared to your actual strength of your material. Okay, so how to explain these discrepancies during during your metal forming processes, or during the forming. So this has been explained by the type of linear crystalline defects, and that has come to be known as dislocations. Okay, so this may be explained by the movement of dislocations. Okay, so today we will try to see what is dislocation, and a kind of dislocation, how it is responsible for plastic deformation. Okay, yes. So as I told, the discrepancy in mechanical strength could be explained by a type of linear crystalline defect that has come to known as dislocation. So these dislocation are basically of two types. One is called ace, and another one is called screw. Okay, so suppose this is a crystal structure which you are seeing. Okay, and we are first taking S dislocation. So in N S dislocation, localized lattice distortion exists along the end of an extra half plane of atoms, which also defines the dislocation line. Okay, so here you can see in this crystal lattice in this localized region, there are these are the perfectly joined atoms. Okay, so this is one row, one column of atoms, then another column, then another. Okay, so here you can see all these are atoms are connected perfectly. This crystal is perfect, but here in this area you could see there is a half plane of atoms. Okay, these are the full planes, 1, 2, 3. Okay, then fourth one is half plane, then fifth, sixth, seventh. Okay, so here you can see in this region, this is your half plane of atom, and when when you are applying shear stress, this half plane is moving from one end to another end. Okay, so how this half plane of atoms moves, this we will see in the next discussion. Okay, so in edge dislocation, there should be some extra half plane of atoms in your crystal structure. Okay, then there is another type of dislocation, that is called the screw dislocation. In screw dislocation, dislocation may be thought of as resulting from a shear distortion. It is its dislocation line passes through a center of a spiral or atomic plane ramp. Okay, so here you can see your number of atoms or planes are fine. Okay, here you can see there is some kind of your edge has been dislocated by twisting or by the application of your shear stress. Okay, so if from in the half portion, your crystal is perfectly perfect crystal, but in this side there is some kind of dislocation. Okay, so due to this, what is happening, this kind, because it is existing in the half, and it is looking like it has been twisted or it has been screwed. Okay, so since the portion is looking like screwed or twisted, we call it as a screw dislocation. Okay, so many dislocations in crystalline materials have both edge and screw dislocation component, and these are called mixed dislocations. Okay, so when we are talking about edge dislocation and screw dislocation, it is not necessarily that the material will have only edge dislocation or material will have only screw dislocation. It may have, or normally it has both kind of dislocations, and that is why the dislocation are called mixed dislocations. Okay, so these are mixed of edge as well as screw. Why here you can see there is we can see screw dislocation existing in this plane, as well as here we can see extra half plane of atom. Okay, so that is why this there may be both kind of dislocation in your crystalline material, and that is why it is called as mixed dislocations. Okay, so how these screw and edge dislocation are responsible for plastic deformation. Let's just try to see. So the two prominent mechanism for plastic deformation, these are slip and twinning. Okay, so maybe you have studied, but it would be a kind of repetition, those who remember. Okay, slip is the prominent mechanism of plastic deformation in metals. It involves sliding of blocks of crystal over one other along definite crystallographic planes called slip planes. Okay, so in crystal, what happens, let me draw here. Okay, so you may have crystal structure like this, and okay, okay, so when you are this may be your crystal, and suppose this is your extra half plane, then something like this. Okay, so when you are let leave right now, leave the extra plane. Let us try to understand which one. Okay, so suppose you are applying shear stress. Okay, so since you are applying shear stress, tau, what is happening? Uh, uh, take this example as your car deck. I think you might have seen a car deck. Okay, so your under slip under slip, it is analogous to a deck of cards when it is pushed from one end, and slip occur when shear stress applied exceeds a critical value. Okay, so let me draw it in different manners. Just a second. Okay, so you can say this is a card rack. Okay, like this. Sorry, card deck. You are having card deck like this. These are card placed one over another. Okay, so when you are applying shear stress, what is happening? These card deck are dislocating, and it is your after plastic deformation or after slip, it is taking shape like this. Okay. It takes shape something like this. Okay. Similarly here. Okay, so this is how the slip takes place in your crystal structure. Then during the slip, your each atom usually moves same integral number of atomic distance along the slip plane, producing a step, but the orientation of crystal remains the same. Okay, so here let me now take uh, one more, let me draw one more figure. So what happens here? Because in the case of slip, what we can see in the overall geometry, your atoms or the plane of atoms, it is getting moved in the direction of your shear stress. Okay, so what is happening at the atomic level? Let me not to draw. I am already having a figure uh, to make it more clear. Okay, so here you can see how your slip deformation, the plastic deformation due to slip takes place. So during the slip, we can say that in the material structure, we are having one extra half plane of atoms. Okay, so this extra half plane of atoms, this we have told here, this is responsible for edge dislocation. Okay, so due to edge dislocation, how your plastic deformation is taking place, let us try to understand. Okay, at atomic level, we are having extra half plane of atoms. This exists here, and suppose we are applying shear stress like this. This has been shear stress has been applied here. Okay, in this particular plane of atoms, and here since this extra half plane is up to here. Okay, so there are possibilities that this particular atom get connected with this atom. Okay, so in the first step, what is happening? Your this extra half plane is getting shifted to your nearby atom, and it becomes a full plane of atoms. Okay, so it is becoming a full plane of atom in the second figure you can see. Okay, but what happens to the vertical plane, your plane of atoms which are already perfect? Now it, since this atom has been connected to your extra half plane, this plane becomes your B plane. Let us read it as A, B, C, D. Okay, so now B becomes your extra half plane in the second step. Okay, so since it has become the extra half plane, and you are applying your stress, because this shear stress has exceeded to a certain critical value. Okay, otherwise it will not be a plastic deformation, and the half extra half plane will not combine with the adjoining plane. Okay, so here we can see, since this plane A has now become full plane, but the B has become the half plane of atoms. Okay, so now what will happen? Your B will again interact with C, full plane C, but here also your half portion of your C will remain at the same place, and your half atoms of B will combine with the half portion of your C plane. Okay, so likewise the movement of your extra half plane takes place, and here you can see the unit step of slip. Okay, so here you could see your extra half plane has come in one side. Okay, so this is happening at the level of atomic level, and if you try to see the in a metal block, how it will look like. Okay, so if there is plastic deformation due to slipping, what will happen? You could see this is the direction of motion, this is shear stress tau which we have applied, and your final component will look like this due to slipping. Okay, so due to slip, the plastic due to slip, the plastic deformation takes place in your metals, and your materials looks like this. Okay, so this due to the extra half plane of atoms which exist in your metal structure, your materials take shape like this. Okay, so here you can see, because we require certain critical value of shear stress in order for the movement of your extra half plane from one side to one end to another end. Okay, so because these are now perfect planes, or okay, so these perfect plane will not distorts automatically, they will not take their original position. Okay, so this kind of deformation is permanent deformation, and for again shifting this unit step of slip from right to left, you will again require maybe shear stress which should be more than your critical value, then only this will shift from right to left. Okay, so this may not be accurately correct that this will get shifted at the same location, this may get shifted at another location also. Okay, so that is why we can say due to slip, the plastic deformation takes place in metal structure. Okay, so this is due to slip. Then try to see, I think during the rainy season all of you might have seen the caterpillars. Any students have you seen the caterpillars? These looks like this. Okay, so I expect that during the rainy season you might have seen the caterpillar, and you might have observed their motion, how they move. Okay, so here I have taken one figure which is representing a caterpillar which appears during the rainy season, and they try to move something like this, that they create a hump in their backside, and this hump try to move, this hump moves from tail to head side. Okay, so this is your tail, and this is head of your caterpillar. So this hump is moving from tail to head side. Okay, so this hump is in the middle of your caterpillar, then it is near to your head, and this is how your caterpillar moves on the earth's surface. Okay, In the similar fashion, you can see your dislocation or the slip moves from one end to another end due to the shear stress. Okay, so here you can see the hump analogous to your extra half plane, and this extra half plane has moved in the middle, then it is moving near to head, and then ultimately in the right hand side. So if you are not able to recall, you can easily recall your motion of your caterpillar, and you can easily draw, or you can understand the concept of plastic deformation due to slip. Okay, let us move ahead. Then next, that is it is you know let us compare due to let us try to see. Okay, this we have covered. Okay, so in screw dislocation, this is for screw. This is a typo error in the heading of your slide. It is screw. Okay, so in screw dislocation, what happens? We are having some kind of screwed portion in your metal structure, and when you are applying shear stress, you can see direction of movement something like this. Your screw get dislocated, and the material takes shapes something like this. Your atomic structure takes the shape something like this. Okay, so since we are applying shear stresses, this due to this screwed portion, your material get deformed permanently, something like this. Okay, so this also requires some that the value should be greater than from a critical value. Okay, so this also this screw dislocation also results in or it is also responsible for the permanent deformation in your metals. Okay, so if you compare these these two types of dislocations, that is edge dislocation and screw dislocation, you can see your end product is your plastic deformation, that is the permanent deformation in your metals. Okay, I will finish quickly. There is one more thing, that is the we have talked about slip. Okay, so then okay, it was correct. Okay, so under slip, sorry, it was correct. Actually, I by mistake I told that the heading is incorrect. The heading is correct. Okay, so under slip there are two types, that is edge and screw. Then we have another type of another thing which is responsible for plastic deformation in metals, that is twinning. Okay, so let us try to understand what is twinning. The portion of crystal take up an orientation that is related to orientation of the rest of the untwisted lattice in a definite symmetrical way. The twinned portion of the crystal is a mirror image of the parent crystal. The plane of symmetry is called twinning plane. The important role of twinning in plastic deformation is that it causes changes in plane orientation so that further slip can occur. Okay, so let us try to see what is twinning. Okay, so under twinning, you can see we have some some kind of crystal structure, something like that, that we are able to find a line in which the one side is one side of crystal structure is mirror image of another side. Okay, so here you can see in this particular type of crystal structure, this side is mirror image of this particular this side. Okay, so from you can say in the one side of your red line, this crystal structure is mirror image of in the another side. Okay, so in this case, how due to twinning, how this plastic deformation takes place. Basically, this plane is called from this plane is called twin plane or twin boundary. Okay, so how this plastic deformation takes place in the case of tuning, let us try to understand through this simple figure. Okay, so this is your you can say initially this is your crystal structure or arrangement of atoms in the crystal in the metal. Okay, so here we can see this at this plane. These are the mirror images, and when we are trying to see, when we are applying, when we are trying to see the effect of shear stress on this twin plane, what is happening? Let us try to see. Okay, so I have tried to elaborate it with a more detailed diagram. You can see when you are applying shear stress. Suppose this is your twin plane. What is happening? These atoms or column or plane of atoms, it starts moving in. Suppose it got shifted by a certain value in downward direction. Okay, so this is representing in the right hand side figure. You can see the movement of your atoms along your slip plane. Okay, so this is also responsible for the plastic deformation, because this movement of atoms is permanent, and that is why the deformation is permanent in the case of your tuning process. Okay, so this is at atomic level, and when you see the combined effect of your tuning process, it looks something like this. Your in the right hand side, that is figure B, you can see due to shear stress applied, the tuning takes place in the atoms, and due to combined effect of atoms, your twinned portion becomes something like this. Okay, but in the case of slipping, slip planes, you can see it, since it is it is analogous to your card deck. So this in the slip, the crystal structure or the material moves something like this. Okay, so this is the figure through which you can compare the plastic deformation due to slip and twinning. Okay, so